Okay, hello everyone, good morning or good afternoon, and welcome to the ISGAN webinar of today, Aggregator in Digitalized Power System. This is Matteo Tronchan and I'm representing ISGAN. And let me introduce you to ISGAN, which hosts this webinar. ISGAN is the short name for the International Smart Grid Action Network, a technology collaboration program of the International Energy Agency. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategic platform to support high-level government attention and action for the accelerated development and deployment of the smarter and cleaner electricity grids around the world. ISGAN currently consists of 28 contracted parties. Their nominated representatives form the executive committee, headed by the Presidium and assisted by the two co-secretariats. ISGAN's vision is to accelerate progress on key aspects of smart grid policy, technology, and investment through voluntary participation by governments in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, user and consumer engagement. ISGAN facilitates dynamic knowledge sharing, technical assistance, peer review, and project coordination among its contracted parties. The ISGAN value proposition relies on conferences and workshops, policy and technology briefs, discussion and technical papers, casebooks, and webinars. Within ISGAN, virtual learning offers the ISGAN community means of rational and continuous technical skill update in the field of smart grids. Virtual learning is proposed as a set of e-learning and reading core modules dealing with the entire value chain of smart grids. And in particular, the webinar today is linked to the ISGAN Lighthouse project, the smart grid distribution powering the energy transition. The theme for the ISGAN Lighthouse project is the electricity network planning and implementation under uncertainty for the clean energy transition, the roles of smart distribution grids in energy systems. The ISGAN Lighthouse project is a global initiative to facilitate coordination between work streams in the international energy ecosystem and relevant stakeholders at local, regional, and national level. The initiative focuses on the co-production of policy guidance and increasing awareness of the pivotal role that smart distribution grids play in reaching the global goals to triple renewable energy generation and accelerate energy efficiency. One important part of distribution grid modernization and enabling the energy transition is finding the solution to increase flexibility. And one part in this finding regards how to find good approach and how to aggregate distributed energy resources. The webinar today deals with the aggregator's role in digitalized power systems. Utilizing distributed energy resources, the flexibility potential of the distributed energy resources from customers is crucial for the TSO-DSO-Customer coordination. Aggregators can facilitate as an intermediary by providing services to different power system participants. This poses new challenges for monitoring, controlling, and coordinating customers and other market players' needs. This webinar aims to disseminate knowledge about aggregators in power system, address the challenges encountered, and share the experience from pilot projects. The speakers that we have today are Professor Sebastian Lenov from Office, Marcel Otte from Office, Jirapa Kamsamsrong from Office, and then Annike Abromeit from EBAS and Christian Kunze from Smart Innovation Norway. The question and answer session will be moderated by Jose Pablo Chavez, that represents ISGAN and stays with Comillas Pontifical University. So feel free anytime to pose your question using the question and answer tool, and then the speakers will answer at the end of the presentation during the roundtable. As usual, the webinar recordings will be available through the ISGAN YouTube channel. Now it's time to give the floor to the speaker. So please, Sebastian, feel free to share your screen and start with
screen.
Yes, we are.
Okay. Yeah. Also, hello from my side. Thank you for being able to present some of our work that we are doing here. You can see the abstract, the rough agenda for today. I now have the pleasure and honor to briefly introduce that middle part here, the aggregator roles in digitalized power systems. And I will start with a brief motivation and introduction, especially now that you heard that three of the presenters today are coming from office. Briefly say a few things about our institute before I hand over to Girappa and Marcel. Yeah, so Office is a German computer science research institute. It's a computer science institute focused on industry transfer. We are now in our 33rd year of doing this. We have been initially funded as an institute to the University of Oldenburg, but roughly 15 years ago, oriented ourselves 90 degrees and focused on application areas. We have roughly 300 employees today and are pretty large for an application-oriented computer science institute. And in the state of Lower Saxony, where we're from, we are the largest federally funded research institute to date. Regarding the application areas, today we're talking about the energy sector, the energy domain. Energy is by far the largest application area that we're dealing with. But we also have an application area targeting manufacturing, digitalization solutions, especially in small and medium enterprises. We're looking at digitalization aspects in the health sector, in the context of ambient assisted living, and also emergency room technologies. And one of our newest additions is actually a society division, where we look at the intersection between society and industrial applications, interface design, but also in digital transformation topics that are then again related to the energy system. Today we are talking about the energy system, and energy research has a long tradition in Oldenburg, and especially at Office, not so much in the technical or traditional sense, electrical engineering, mechanical engineering, but always from a systemic perspective. So in the 80s, we started with energy metrology, climate models, but then pretty much also started in looking at the role of the digitalization sector with many milestones, where we started with lighthouse projects, large transfer projects. And today we have the largest energy informatics team, at least in Germany, with roughly of 100 researchers looking at digitalization topics in the energy sector. We're still not looking into electrical engineering, but only in various variations and different variations in challenges with digitalization in that context. Yeah, and that basically brings me to the topic of today of aggregators. When looking at the three major trends that influence this transition from the classic vertically integrated energy systems to a decentralized, liberalized, and especially digitalized energy system, we are talking about distributing, decentralizing many things, coupling different sectors to it. But in the end, we need to come up with ways and means to actually orchestrate the largely distributed, self-organized consumption as well as the production side. So that's something that's really different, and also that sets not just Germany, but some parts of Europe as well, apart from other places in the world where, of course, the energy transition plays a role. We're doing it everywhere at the same time. So consumption side, production side, digitalization side, everything is now transformed at the same time, with all the challenges, the caveats, and the problems that you can imagine, from questions how to safely and secure such a system with technologies that are by definition not safe and secure. The question of not just implementing it, but before modeling, simulating, and testing it. And of course, all the related and subsequent questions when we talk about optimizing, operating, and training personnel with this kind of transition and digitalization in place. One of the key aspects that is important in order to make this possible are aggregators. The concept of aggregators is by no means new. It's as old as the energy transition itself, when we talked about substituting large power plants with smaller distributed generation devices or generation units, because we had to overcome market entry barriers. We had to deal with the stochasticity and the fluctuating generation. And one way to deal with this, or the original way in dealing is pooling. And so basically pooling, aggregating distributed actors such that they can, well, better deal with existing market mechanisms, platforms, but also stabilize distributed, highly stochastic, fluctuating resources by pooling them and getting some stability in the stochasticity behind this is one of the key aspects behind aggregators. But there are still challenges that arise with this aggregator concept, and this is something that some of which we will talk about today. That is the interoperability, and alongside with this, the cybersecurity aspect, because we have many different aggregator concepts, many different aggregator implementations, and in order to have them seamlessly interoperable, we need to make sure that they follow standards, not just in process standards, but also in implementation standards. We need not just horizontally orchestrate these aggregators, but also vertically, because in our system we have the TSO talking to several layer DSOs, and in all these DSO levels, aggregation of units through aggregators plays a role. And then if we have, in one of the key examples that also Marcel will be addressing later, is then, for example, something like redispatch down to the low voltage level, means that we have to impose a high degree of automation across these different levels, again, stressing the need for interoperability and standardized communication processes. We need to engage the consumers with this. So basically have the consumers agree to delegate control of not just their devices, but also the data that is related to these devices, of course, then directly related to the concepts of data privacy and trust. And again, yet again, we need have to look at the regulatory framework because it provides the umbrella, the frame of reference for all of these different implementation and instantiations. And the work that we are presenting today is actually, or has investigated and discussed how aggregators can improve this TSO-DSO customer coordination in digitalized power systems. And that's what we are looking at today. Yeah, and at this point, I would like to hand over to Jerapa Kamsamrong. Dr. Kamsamrong is one of our group managers at Office, and she is leading our smart grid testing group, especially looking at the, I would say, last mile before when we develop solutions, and also these aggregator concepts before we bring them into practical reality, into real laboratories, into test instantiations at customers, at DSOs. And Jerapa is going to outline the existing policy framework in which that work we are talking about today is actually taking place. Yeah, Jerapa, with those words, I would like to hand over to you.
Thank you so much, Sebastian, for the introduction and the motivation of our work. I will share my screen. I hope that you can see my screen now.
Yes, we can.
Yes.
Okay.
Yes.
Great. Okay. Let's have a look for the existing policy framework for aggregators. I think some of you may have heard about this European Union Directive 2019/944. This regulatory framework had defined the aggregation terms and also independent aggregators. What does it mean here? The aggregation term can refer to the action, and the independent aggregator refer to the actors. When we have a look into this term for the independent aggregator, it defined as a market participant engaged in aggregation who is not affiliated to the customer supplier. What does it mean here? It means that independent aggregator is not supplying anything, for example, energy to your house. So it's solely independent from any service that you have with your energy companies. This regulatory framework also introduced the demand response concept and also citizen and renewable energy communities. In here, we can see that the aggregator can play more role to support new energy service to energy communities. However, we have the umbrella for the European regulatory framework, and each country in the Europe should transport this regulatory framework within 2 years. And now it's already 4 to 5 years when we can have a look the status of the transposition of this law in Europe. This slide, as you can see from the map, a study from Joy Research Center, and this study is from 2021. So it is a little small remark here that the status might not be up to date, but I could expect that there will be more development about the aggregator demand response in another countries as well. So as you can see in the map here, in the study, they have found that 85 countries in Europe already have implemented the demand response. And the main challenge is that only 7 countries that highlight in the dark blue only implement the demand response with independent aggregator for the small customer, for example, the resident customer. Why is that? They have found out that there's some technical challenge, mainly from adopting of smart meter rollout in some countries. And in some countries also face some kind of like regulatory challenge because the new and the small aggregator actor has very high market requirement. So this is something can be a non-technical challenge for them to enter to the market and provide new energy service to their customer. In our paper, we have a study for 5 selected countries in detail about transposition of this regulatory framework, and also give some example for the aggregator services in some countries as well. But in this webinar, we have very limited time. So I would like just to showcase one of the 5 countries, which is Germany. Here, the example for the Germany, we have existing regulatory framework that support the aggregating services. For example, Renewable Energy Act and also Energy Industry Act. So with this law, aggregator can manage customer flexibilities and also supply to energy market. They can also participating in the congestion management with the Redispatch 2.0 framework. Aggregator can offer their services to distribution system operators for managing their flexibilities, but these regulation have addressed for the generation unit of more than 100 kilowatt. However, there's some research project have addressed the potential of the smaller unit of the lower than 100 kilowatt. For example, the Dispatch 3.0 project that coordinated by office. So we're trying to explore the solution and also the goal to integrate these smaller unit lower than 100 kilowatt and also TSO-DSO coordination approach for this congestion management. There's more regulatory framework in Germany. For example, last year, Germany has started the law of restarting digitalization of energy transition to roll out smart meter. And start from this year, the agile approach has already been implemented, and we expect 95% of customers with the consumption over 100 kilowatt hour per year, or the generator over 100 kilowatts must install smart meter by the end of 2022. And not only this, recently, if you may heard, start from January this year, the paragraph 14A allow the power system operator to dim the power consumption of the customer system, such as electric vehicle, energy storage, photovoltaic. So we can see that the law in Germany has been engaging more and more at the end user, especially at the low voltage system. And we can see that the aggregator can play more role and also offer the new service to the power system in Germany, and also encourage the customer who is already the typical customer and want to become to the active customer. So this kind of the regulatory framework would enhance the aggregator model in Germany in the future. And as we can see that the aggregator can provide many services to many market participants, for example, DSO, TSO, and also the customer themselves. And this is something that we have addressed. There might be some technical challenge because of they can have the several coordination approach among them. And I think that would be meaningful for us to have a look what kind of approach that's possible, and then you can apply it to your own countries. And I think Marcel can walk you through this content and the presentation for the aggregator role and the coordination approach. And I will give the floor to Marcel. Marcel, the floor is yours.
Yeah, thank you. Hope you can see already my screen.
Yes.
Okay, nice. Yeah, thanks, Girappa, of course, for introducing us to the European directive, and we will now dive deeper from the policy perspective into the technical perspective. Therefore, this part will be now focusing on the roles of aggregator and how aggregator can be implemented from a technical point of view. As Sebastian mentioned already in the beginning, aggregator concepts are not that new, and along with aggregator, the concept of virtual power plants is usually there. The virtual power system is nothing else than combining a lot of small distributed energy resources, such as biomass, storage systems, wind parks, solar parks, or as well the active customer itself. And combining them is a so-called virtual power plant. This concept is usually applied by aggregator, and as we saw in the European regulation, it's that these distributed energy resources can now be transferred or by the aggregator provided to any electricity market. The focus of this work, however, will be the active customer. Why is it so special? Because it's in low voltage systems, and usually a lot of people are there, and demand and storage and generation is there, which means, for example, there's a heat pump installed, or in this case, photovoltaic system in combination with electric vehicles. We have seen a similar representation of this figure by Sebastian, now with the services added. This is based on the USEF framework, which is widely adopted in the energy system or in the energy literature. And there you can have a nice overview of what kind of services are there. And as you can see on the left-hand side from the aggregator, you see the active customer and the aggregator as a kind of man in the middle who provides the flexibility to any of the market player on the right-hand side, which can be the TSO, the DSO, or as well the balancing responsible party. You see here 4 different categories, which can be, for example, constraint management, as we had for congestion management, for example, low voltage services, or you can have adequacy, where strategic reserves, or for example, load shedding is one example which an aggregator can provide, or at the wholesale market, which is very famous for, let's say, these dynamic tariff options, and as well for balancing, where you have to have harder regulation. However, if you apply it, you can get a higher remuneration. So aggregator can offer new services to other market participants, but they are not limited to only one business model. So it means they could combine the flexibility for, let's say, the wholesale market and the balancing market. So the example will be at the TSO level, they can provide the balancing market, or TSO level for congestion management, or to another balancing responsible party for day ahead and intraday optimization. So the customer is then in the role to become active. And in the EU regulation, as Girappa mentioned it, it's as soon as the customer is open to provide the flexibility, it can become active. That's why the regulation is nicely having this kind of word, because it summarizes as well prosumer or people who have only flexible loads. So how does it look like? We will now dive deeper into an example. So let's say, because dynamic tariffs are kind of famous at the moment and they are becoming more and more rolled out in several countries. So let's assume we have an aggregator or an energy supplier, but in this term, we will call it aggregator, providing dynamic tariffs to the energy management system of an active customer. How does it look like technically? So let's see on the x-axis the time of the day, and on the left-hand side the power in kilowatts. We have usually non-flexible loads such as hairdryer, vacuum cleaner, and so on, which are not so applicable to demand-side management and other services. However, we have flexibility 1 for this household, which is a photovoltaic system. We have flexibility 2, which is the electric vehicle. And as soon as the aggregator comes in place and identifies, for example, time frames with low prices, the energy management system has the capabilities, for example, to shift the energy demand to the zones where the low prices are. So this small time shift is applied by flexibility 2 from the electric vehicle. So the demand is shifted. So the energy regulation says as well that, for example, what the Joint Research Center from the European Commission says as well, that customers should be allowed to have multiple contacts with different market participants without foreclosing the other. And there comes the independent aggregator in place, which Shirapa mentioned. I will explain it to you on the same example. So we have seen that the aggregator shifted the demand to the low price zone, and we have now a second aggregator who is the independent aggregator in that case, because he's not affiliated to the energy supply and can provide the service as well to the active customer. Let's assume we have a balancing service provided by aggregator B, which is as well an example in the Joint Research Center. So basically, we have identified, for example, for aggregator B, a time frame where demand response in terms of we have to reduce the power output in order to stabilize, for example, the grid frequency. So basically, in this low price volume, aggregator B says as well, please reduce your power. So it reduces the power, and both aggregator provided a service. But what does it mean? We have identified the independent and the not an integrated aggregator, and from the policy perspective, as soon as both are implemented, we can deviate or differentiate it based on the aggregator implementation model from Ignukulo. So basically, in order to fulfill the requirements for having, for example, 2 aggregator, you need to assign one who is supplying the energy, which is on the left-hand side depicted as the integrated aggregator, which is an aggregator that supplies the energy as well. If it's not affiliated to the supplying energy, we have this so-called independent aggregator. You can further differentiate on this approach, like making as well the responsibilities for the balancing responsible parties, and as well differentiate if it's a flexibility provider or not. So on the left-hand side, for the integrated aggregator, you have the aggregator supplier model, which I already mentioned is some aggregator who provides as well the energy to the end customer. And on the right-hand side, you see, okay, there's a second aggregator in place, this independent one. Are there 2 or more balancing responsible parties for that, or is this in the balancing group? So we have the contractual aggregator, so the first aggregator and the second aggregator, they have to define a contract, because if one aggregator activates the flexibility, it will influence the balancing group of the integrated aggregator. On the other side, it could be as well that there's only one ERP, which means that we have the delegated aggregator or the aggregator as a service provider. And the aggregator as a service provider is someone who only provides access to the device itself. So it does not provide the flexibility to the market, only the interface to it. An example could be the automotive industry. As soon as they have control over all the electric vehicles, it could be that they act purely as a service provider, that an external aggregator can there have access to the flexibilities. But as we have seen now how the aggregator looks like from a technical perspective and how the example showed the integration of active customer, we have to dive deeper why the coordination is so crucial for that. So how to coordinate aggregator and the power system is the discussion for the next part, where we will see how to integrate them first and how to coordinate them. So first we have to understand how the power system looks like. So we have the traditional power flow, as Sebastian mentioned in the beginning, from the top till down. What does it mean? On the right-hand side, you can see the typical power system from the past, which was that the generation to the customer was like a top-down approach, and the energy flows from generation to the customer premises over the transmission grid and over the distribution grid. Now, with more renewables, you are replacing the generation units which were coal, gas, and etc., and have clean technologies integrated. And depending on the size and type, you locate them in different places. For example, on the generation side, you can as well having large wind parks, for example, offshore wind parks, or you can have very large hydrogen power plants as well connected directly to the transmission grid, similar to the old and traditional power plants which you had before. But as well to lower levels in the distribution grid, which you see often, for example, smaller wind parks or photovoltaic systems, which you can see that they are directly connected to the distribution grid, but not on the customer premises. On the customer premises itself, it's also, of course, possible, as we said all the time, it's the active customer or the customer who can become active through aggregation. So the aggregator itself then, as we saw for the virtual power plant, has access on different voltage levels and may integrate in their virtual power plant different kind of distributed energy resources located on different voltage level, on different grid operator levels, and could be as well at the customer premises. Therefore, to have access, they usually have different systems, which are, for example, the energy management system, where they schedule their virtual power plant. So they have this kind of operation of their virtual power plant. They select the resources and identify how they can trade it on the market. You see the domains are donated here from generation to customer premises. We will now take this depiction a little bit more into a technical perspective and have as well a differentiation on the y-axis. On the x-axis, you see the generation, transmission, distribution, DR, and custom premises. But now we have on the y-axis as well from the process level to the market level. You don't have to understand it in detail. The only important thing about that figure is that it's a different if you talk from market level on to another market level, because then you have different interfaces and different communication technologies comparing, for example, to an aggregator who communicates to the household. Because from a system and technical perspective, that is important if it's an edge device, if it's a server room, and so on. But for this depiction, we have now compare different coordination approaches. Therefore, we can focus on the market level and the process level. First, the customer itself will be simplified by our house, which we saw before. I will now go with this PowerPointer and hope you can see it nicely. For the centralized flexibility market, we had it in the past years as well, and it's still for balancing markets the case that the aggregator in here combines the active customers and trades them on the transmission level to the TSO. So the TSO and aggregator are directly then in the contract phase where the virtual power plant and the flexibilities will be offered to the TSO. However, as you can already see, the DSO will be not part of this process where it be covered in the market. So therefore, you can see in here that the flexibility market, they select the resources at TSO, and it could be optional that the DSO identifies if it's possible or not for the DSO. So what does it mean? So the aggregator, let's say, combines thousands of electric vehicles in a specific DSO area and provide it as flexibility as a transmission grid. If the transmission system operator says, okay, I want to activate these flexibilities and go ahead with that, then it could be likely that, for example, the DSO identifies congestion because if everyone charges at the same time. Therefore, this centralized market can have like the drawback of that validation does not take place and leads to congestion for the DSO. But as I said, the centralized flexibility market is still placed and was from the history a lot of time, or in the history, you see them a lot of times. Compared to that, we will go to the second coordination approach. These coordination approach, by the way, are identified in literature from the paper called the coordination approaches, which are identified in different research projects. It was done by Silva et al. And we now put the coordination approaches more onto a technical level and identified the current European regulation and placed them as well in this context. The second opportunity where coordination can take place is like if you have a local and a global TSO flexibility market. What does it mean? We saw before in the model 1 where the aggregator trades the flexibility and provided it to the transmission system operator. We now provide it locally. This could be as well for congestion management or other flexibility markets. However, you can see that the distribution system operator first selects the flexibilities provided by the aggregator, and the remaining flexibility will be then procured by the TSO. You can see now in this coordination approach that the resources are shared, but the DSO selects first. And even if the TSO selected the remaining flexibilities, it could be that the DSO validates if the selected flexibilities by the TSO will cause any issues. This could be the situation where the DSO, an example, demands that the aggregator should reduce the power output, but the TSO simultaneously says, I want to do it vice versa. I need more power in the grid to stabilize, for example, the frequency. There are more coordination approaches, which could be as well that the DSO and TSO have shared responsibilities, but predefined agreements. What does it mean? The aggregator still offers the flexibility locally to distribution grids, but the TSO itself will not do it directly. So there's no direct connection between the aggregator and the TSO for this flexibility market. But the DSO and TSO beforehand identify predefined schedules. For example, that the DSO is allowed to procure flexibility in a specific range without causing any influence on the TSO level. Compared to that, we have a common TSO-DSO flexibility market as a further opportunity. So the aggregator itself talks to the DSO and DSO simultaneously because they have a common flexibility market. And the common flexibility market would require that the TSO and DSO select their resources from this common energy flexibility market coordinated. So both selected in a coordinated manner. So what as well was identified is that you're not only having the aggregator who coordinates with the TSO or DSO and the active customer itself, but also that the new European Union regulation identifies as well that you have the energy community concept. What does it mean? For example, we have an aggregator who combines all the customer from the low voltage grid and provides a so-called energy community, which could be that active customer A, for example, has an excess of power from the photovoltaic system, which they inject into the grid, and active customer B wants to consume the energy from the active customer A. Therefore, the aggregator can provide this kind of platform in order that they can exchange their energy. For example, you can call it as well peer-to-peer trading or the concept of energy communities. The further approach is a so-called over-the-counter approach. In some markets, like the over-the-counter approach, which means that an aggregator or another market participants talk to another market participant without having it on the market level. It's more that they have directly contact to each other and identify, for example, that both aggregator have an added value if they combine their flexibility and share, for example, that aggregator A has a lot of electric vehicles, aggregator B has huge wind parks, so it makes sense to have an over-the-counter approach. So aggregator-to-aggregator communication is still possible as well, besides having the DSO and TSO as one of the main user of the flexibility. So we saw now always the active customer as one thing which was only depicted as these picture with the electric vehicle, the energy management, and the photovoltaic system. If we place now the active customer in a similar manner, how we've done it before with the aggregator, DSO, and TSO, we will now focus as well having the same y-axis for the active customer itself. So how does the active customer usually look like? We try to have it very general because you have small deviations from each country to another. But in general, the flexibility comes from controllable load, from storage, depending on if it's an electric vehicle or a battery storage system, which is at the household, or generation, which could be here, for example, the photovoltaic system on the process level. Usually it makes sense if you have multiple flexibilities to use an energy management system at home, which is quite common. And as soon as you have these, for example, self-optimized production that you want to inject less energy into the grid because self-consumption makes more profit for you, then you have the battery, then you have a solar system and the battery from your household, and therefore you can combine it and make schedules and try to use or optimize it as much as possible. And now, as soon as we want to have access from external, the smart meter rollout comes in place. We depict it here as a meter and as a gateway separately, but they can come in a single house, as a single device. Some countries have it that you can fix it on the meter, but in here we depict it now a little bit more general. So the meter itself is that what counts for the energy, and the gateway is from, in Germany, it's, for example, the smart meter gateway, but in other countries, it's directly on the meter itself. But now we say we use this gateway in order to have access to the energy management system. Therefore, we would require a connection from the energy management system or the controller of the device to the meter operator. The meter operator is here simplified depicted. It can have multiple systems behind it, but for simplicity, we just use the icon for the meter operator to avoid very complex pictures. So we have seen the coordination on the market level with DSO, TSO, other aggregators. We have seen now the integration, how an active customer looks like, which is depicted on the right-hand side. And here we will now focus only on the energy management system and the DSO itself. This is also on operation and not on market level. Therefore, the market level is not depicted anymore in here. But now we will focus on who coordinates in the case if, for example, a DSO or aggregator wants to activate the flexibility in the grid area of a DSO. We identified 4 different possibilities. One could be that the aggregator coordinates the control signals. So everything which is depicted here in orange is the control signal, but maybe you are watching it not on a huge screen, therefore it could be that you cannot read it, but the orange arrows are always the control signals. So as soon as the aggregator coordinates the control signals, it means that the DSO can forward the control signal to the aggregator and say, for example, please do not charge more than, let's say, 10 kilowatt. And the aggregator then has to realize this flexibility on the active customer, either using the gateway itself or through the direct connection to the energy management system, which happens in a lot of countries, that there's not the way through the smart metering system, but regulation often foresees that the way through the smart meter gateway or through the advanced metering infrastructure has to be realized, because you can now already foresee that as soon as they communicate through the backend system, it's easy for the aggregator to integrate, for example, the energy management system. Let's say because the manufacturer of this energy management system is the aggregator, then they have this proprietary interface. But it's for the active customer sometimes not foreseen that they want to have this solution, because it would mean that they are bound to the products of the energy management system provider. And therefore, these communication through the gateway itself is often in countries foreseen. But as it's as well required, it requires that the aggregator and TSO have a direct communication between each other, which means that the distributed management system and SCADA system not directly connected to the energy management system on the aggregator, but they need kind of an interface and coordination approach realized. If we focus now on the next approach, it would mean that the aggregator itself does not have direct connection to the energy management system or the controller of the flexibility. It would mean that the aggregator demands flexibility and says to the DSO, please control the device because it's my customer. This concept is was rarely seen in some countries, but it is well written as a concept there, but I haven't seen it yet realized that way. But as I said, it's only a concept which we want to show, and we do not want to say which one is better. We want to see which possibilities are there. Coming to the next approach, we can have as well that the meter operator controls the signals. So basically, the DSO and the aggregator have access through the flexibility through the smart meter gateway. This is what is currently rolled out in Germany a bit more. So the DSO, for example, says I have a congestion and says it's through the gateway, and it means that the meter operator takes care about this coordination. So it could be that the priority is always that the DSO controls, and as soon as the DSO has not any demands for this flexibility, then the aggregator can do whatever signal he wants to forward. And then behind everything, there's interoperability already given, and the communication through the gateway and through the energy management system provides already the coordination. And yeah, then the fourth and the last coordination approach which we identified is that the energy management itself has the opportunity to receive signals from different market actors and receive it either directly through the gateway, or for example, the situation which we had before, that the aggregator has direct access to the energy management system and not through a gateway or not through any metering system. But in this, the energy management system is able to identify from different actors how they should react and how to find a suitable solution. And with that being said, we have seen that for all the approaches, we use always these layers. So we saw from generation to the customer premises from the beginning that we have the different domains. We have as well seen two different zones. So we saw, okay, electric vehicles could be as well located on the process level and are not directly on the market level, because systems and technology between it has to realize that you can provide this electric vehicle to the market. In order to achieve a holistic approach and interoperability, we have to think about all the dimensions which are possible for these use cases and for the aggregator coordination. So basically, on top of this layer, we have the communication layer. What does it mean? It means that we have to identify which protocols do we use. For example, do we use any standardized protocols? For example, we can see later on in the presentation from EEBus how this is realized. Then we have to identify which data is exchanged, because sometimes you're not getting all the data which you require, or you have to verify which data you require. For example, from the electric vehicle, which I mentioned, it has to be realized which state of charge does the electric vehicle, do I even need it, or do I need any schedules, if I can even have schedules, or is it not possible because we having households and they do not behave like power plants which have a schedule. And on top of that, we have to outline the use case itself. For example, one use case could be providing vehicle-to-grid services using the aggregator. And then we have to define the use case and identify which data model we use, which protocol, which components are involved. And on top of that, the business layer. So which business objective is aimed? It's not that you directly have to insert a business model. It's more like the business objective in general. With that being said, I hope it was not so technical or too technical, but we are coming now to the next part, which will be presented by Girappa again about the challenges and possible enablers.
Yeah, thanks again. So now we have learned about the coordination approach that there's so many approaches that you can apply to your country context. And yeah, in our study, we did the survey and also the data research from the pilot projects that implementing about the aggregator and demand response. It should be noted that our challenge and key enable here is very high level evaluation approach, and you can apply to your country context and further research and identify the best solution or the appropriate one to your country context. Let's have a look for the technical challenge. As you've seen that we have many approaches to coordinate between aggregators and other market participants, for example, DSO, TSO, and also aggregators themselves, and even though to energy communities. We could see that if the aggregator provides some kind of like their proprietary protocol solution, this could pose the technical challenge about the interoperability and also the interface between the system. It's not only that, they could also limit the freedom of choice for the customer as well if they want to switch from one aggregator service to another one. The interface between their solution should be standardized and interoperable to enable the plug and play solutions. Yes, as we are aware that there's ongoing about the smart meter rollout in many countries, and we could see that the low adoption of smart meter rollout could limit to the aggregator service to provide some kind of like demand response, direct load control, energy management system. So we could see that the ongoing about the grid modernizations and digitalization could also support energy service provided by the aggregators. And also, the aggregator can encourage the traditional customer who only use electricity to become the active customer. So they can participate in energy system, how to manage their energy consumption in their home, and participate in some kind of like incentive pricing, dynamic pricing that aggregator or the energy company can provide it to them. So we were seeing that the ongoing energy transitions open up new opportunities, but it's also posed the challenge about the cybersecurity as well. So we are aware that aggregator and auto market participants must follow the standard about the cybersecurity to provide some kind of like the secure services to the customer and ensure that there's secure interface between the system, between aggregator and other energy provider solutions. This is also ensure the trust of the customer when they want to use the new energy service from the aggregators. And of course, there's a growing demand for cybersecurity workforce for providing cybersecurity support to the new energy services. These can also building the trust from the customer using that service and for the long-term engagement. So this is the overview of the technical challenge that we have identified from the pilot projects and the research project from other countries. And we also have addressed not only the technical challenge, but non-technical challenge as well. Normally, when we implementing the new technology, we're going to look at technical, economical benefits, how we can integrate them, how much that's going to return to us. But we mostly neglect about the consumer perspective. What does it mean here? Because we introduce the new energy service to the customer, and of course, they might have to adopt new knowledge about the new technologies. Many studies have shown that the social norm and appropriate data also could induce some kind of new energy practice among them inside the society or inside the community to engage them to participate in energy system. So this is something that it could establish a new kind of the energy service and energy practice provided by the aggregators. And also the concerns about the data privacy and consumer acceptance. Some studies have revealed that inappropriate data perceptions and long perception about the technology could lead to the oppose of the new technologies. For example, when we talk about the smart meter, the term of smart can be intriguing for them, and they might think that it can help them to save energy and the money by doing nothing. So this is some kind of like wrong perception that the government and the policymakers should aware of this, that we should provide some kind of like knowledge and increase awareness of new technology to the citizen. This is to ensure that we build the right way of the trust and also the engagement for the customer for new energy services. And yeah, the regulatory framework for sure can ensure this kind of implementations. And not only this kind of the challenge, we also see that we should include the knowledge building. And for the student, of course, because the digitalized energy system require interdisciplinary skill workforce to support new energy services provided by the aggregator or another actor in the futures. So education curricula should be reviewed and updated regularly to provide up-to-date knowledge and also provide practical knowledge to them. So this workforce can support our energy transition in the future effectively. And also, yes, I already mentioned that the awareness and information of new technology for citizens is quite essential. So we should start this one as soon as we want to introduce the new technology to the citizen, because the process requires time and it's not happen overnight. So it needs some time to build the knowledge up for them to understand what is the real benefit, how they can apply their behavior to use the new technology. So this is take some time for them. In our study, we have addressed the challenges for technical and non-technical one, and we have identified some kind of like possible enabler. And this is not something that is a must, but it's some suggestion that can be applied in any context. But in which level and granularity of the policy instrument should be designed for the consumer context and the energy system context in each countries. For example, the technical challenge, of course, is very essential for standardization, interoperability that could help for the interoperable and secure interface for providing new energy services. And also high adoption of smart meter could also help to increase automation capability. An aggregator can access the customer flexibility and can provide this potential to energy market. Also, building cybersecurity culture in the organization, in the company, also could strengthen for cybersecurity knowledge and the number of the workforce. While we trying to have new energy services, new technology and solutions, the R&D projects such as the pilot and the regulatory sandbox can support to demonstrate this kind of the innovative solution to the customer and also to the policymaker, like what we have learned from the project and what we could do it better. And yes, the regulatory framework is one of the key enabler to ensure everything. For example, like first of all, freedom of choice for the customer, that they have the freedom to switch from one to another, and to make sure that the technical requirement can make it happen, and for the seamless switching from one to another one. And yes, with all the challenges, also the education and increasing awareness for citizens and new workforce in the future is very important. So we could ensure that what we are doing or what we're trying to offer the new services from aggregator could increase a system value as a whole. So here is the last slide of our presentations. I would like to summarize and give some key takeaway from our study. In the European Union, we have an umbrella policy framework that can support independent aggregators, but each country have to transport this law to their national law to support aggregator role and service in their countries. And policy framework should be in place to support new energy services provided by the aggregator. Also, providing technical requirement, fair competitiveness, transparency, and also freedom of choice for the customer of using the aggregator services. For sure, proactive policy design should consider both technical and non-technical challenge when they have to design a kind of the policy instrument that could help the country that going to implement something about the aggregator framework to achieve a system value as a whole. So I think that's it pretty much about it from our study and our dissemination about the aggregator roles in the power system. I would like to end our presentation here, and we are looking forward to your question during Q&A sessions at the end of this webinar. And thank you so much for your attention.
Okay, thank you, Irapa.
I hope you can see the screen of the presentation. Well, there is no film, so I guess it's this again.
We can see it. Yeah.
Okay, great. Yeah, hello from my side. My name is Annike. I'm working for EIVAS, and today I'm going to present you the role of standardization for interoperability in the communication in digitalized energy systems. First of all, I want to give you a short overview about the EIVAS membership or the structure, because we're a non-profit association, and we have more than 60 members, which are cross-industry associations, as well as leading companies of the energy industry, which you can see here. And then I want to give you an idea of what we're actually doing and how we are working. So as I said, we're an association. And in our association, we work in working groups with our members, who are quite diverse companies from the energy industry, from manufacturers to grid operators to energy management system providers in the domains of automotive heating and air conditioning, decentralized energy storage, and also generation. We define in our working groups the information flow from one device that is energy relevant to the next device, and specified on the information layer and the function layer, which means that we have developed a data model on the yellow layer that you can see here. I just inserted the picture because it was mentioned in the previous slides, and I guess it helps to understand where we are actually active. So we have a data model for the yellow layer, for the information layer, and we have defined and specified use cases together with our members that are ranged in the blue area. We have also defined a specification for the smart home IP to transfer our information and data model via SHIP, smart home IP. This is a recommendation, but that's actually not an obligation. So EIVAS is transport neutral. It can use any protocol to be transported. So this is one of the main parts, our specifications, and it's also our main output of the initiative. We are testing this protocol and the use cases that is implemented in devices and system in research projects and also in our living lab in Cologne. And we standardize this interface or these use cases and the data model in the relevant standardization committees on national as well as on international scale, to then set up an interface or several interfaces for all energy relevant signals and for the exchange of those signals. Because why is that relevant? As already mentioned before in the previous presentations, we have seen different actors that are influencing or that want to influence those devices that are behind the grid connection point inside the building. If there is more than one actor who is sending signals to change the behavior, the consumption, or the production of certain devices, the building and the device in the end has to know which signal it has to follow and how it can prioritize those signals. Therefore, EBAS has developed a standardized interface at the grid connection point where there's a clear prioritization of signals so that the end device or the energy management system, that is kind of the control management system inside the building, has an idea of how to implement those signals. To give you an idea which devices and systems are involved and in which scale, I guess this picture helps. So EBAS can be applied in single homes, but also in multi-story or commercial buildings. We see the energy management system, the EMS, as the heart of the building and the heart of the orchestration of signals, and everything that is received by the market or by the grid operator is then to be coordinated by the energy management system. In this picture, we have applied the interface from the building to the grid operator and market actor via a gateway as an, let's say, international approach. In Germany, as you have already heard before, it's a bit more complicated. We have the smart meter gateway here with certain requirements and certification processes and functionality scopes, which I will go into a bit more detail in the next slides. First, coming to our EBAS use cases and solutions. This is a table to give you an idea of the different domains we are addressing, the different purposes. So we have use cases that are defined, specified, and also standardized in various committees and standardization groups for power monitoring and control, for flexibility provision, for the grid operator, market operator, or for self-consumption optimization. We have use cases to enable comfort and information flow, and use cases to set up the system. Once you want to connect devices, plug and work together, you have to set up the ecosystem inside the building with these use cases. If you combine these use cases in a smart way, we have defined solutions. So in a certain way, those use cases all make sense once they're combined together in certain contexts for certain purposes. The solutions conclude the grid protection, the dynamic pricing, a solution for grid resilience, and for energy independency. As you can see in the picture here, we have the grid interaction, so the grid operator who is accessing the energy management system. We have the market interaction who is accessing the energy management system and connected devices, and the end customer, let's say in the center of the device operation, all with their different use cases and solutions that serve different actors. Starting with the power limitation, we've already heard before what is happening or what the development in Germany are. The power limitation from EBAS perspective is a bit more comprehensive, but I will also give a short overview what it means for the German market. So with the power limitation, we actually address the behavior of the total or entire building when we when we influence the consumption or the feed in at the grid connection point. Or we can also influence or change the power consumption and power feed in of a single device. So there are different ways to address or to implement this solution. As I already mentioned, the limitation can relate to the consumption or to the feed in. So if there's a surplus of energy, you can also, as a grid operator or aggregator, set a power limitation for the feed in of a single device or of the entire building. And if there's a lack of energy and instability in the grid, you can set power consumptions and times needed With the EBUS use cases and the solution, you're also able to see what is happening, how the devices react upon these signals. So you have measuring values that are indicating if the device is following and the grid connection point is behaving upon the power limitations. As already mentioned before, there's a new law in Germany of the Energy Industry Act defining that devices have to be controllable by the grid operator. Those devices concerned are wall boxes, heat pumps, air conditionings, and storage units with the power over or off and over 4.2 kilowatt. In the EBUS solution, it's pretty self-explaining, but we also, we have already tested this solution and it's actually working. The grid operator calculates the power limitation. Let's say it's 4.2 kilowatts here, sends it to the grid connection point in Germany, sends it to via the smart meter gateway to a control unit, which then sends it or forwards power limitation to a connected controllable device. Or if there's an energy management system and several connected devices, then the energy management system receives the power limitation and then spreads the limitation or the signals among those devices that are connected in a way that the overall power limit is fulfilled. While doing so, in price incentives or market mechanism can still be kept. So devices and the energy management system can still react upon a logic of incentives provided by the market operator or the aggregator. However, it has to make sure, or the energy management system has to make sure that those tariff information or incentives are fulfilled under the limit of the power limitation sent by the grid operator. Then we have the dynamic pricing, where variable tariffs can be sent from the grid operator or the market operator or market participant, let's say an aggregator or energy supplier, to the grid connection point and then to the single controllable devices or to the energy management system once there's more than one controllable device. And those variable tariffs can be based on power exchange market prices or the share of CO2 in the power mix or grid fees that are calculated by the grid operator. And here you have the same logic, the grid operator, or if it comes to dynamic grid fees, or the market actor, if it comes to dynamic prices based on the power exchange market, can send those information via the EBUS use cases to the single device or to the energy management system via the grid connection point in the gateway or grid gateway. Then we have the flexibility provision solution, where we can also have two different dimensions. One is on building level. This could be a solution that might be used by the grid operator, who can send a power envelope, which means a maximum and a minimum range for a certain time, to send it to the grid connection point, to the entire building, so that the entire building or all connected devices behave according to this power envelope for a certain time that is given by the grid operator to prevent the grid from instability. Depending on this power envelope, there is a feedback from the grid connection point or from the energy management system, which is a power demand forecast. So if I'm a building and I receive a power envelope, and I can give my power demand forecast to say in how far I can fulfill it or in how far I need to receive a new power envelope to be realistic and to behave within this range. This can also be fulfilled on a device level. Here, the power envelope is sent to a single device. If there's not more than one controllable device, this could be a solution. It's the same logic. And here the solution serves for also already mentioned use cases such as energy trading, for frequency containment reserve, or for the wholesale market, such as intraday or day ahead markets, where where an aggregator can use this communication or this use case to define or set and control a device in the limit of a certain minimum and maximum of power range. And then there is the self-consumption optimization solution for, let's say, the end customer to optimize his own or his self-created and self-generated, let's say, PV electricity or PV power, so that all devices can react upon the availability of power once it is given. So let's say charging when the sun is shining would be a use case where the electric car or the battery storage consumes energy out of the self-produced PV power. To give you an idea how all these different solutions work together, as I mentioned, there's a need for coordinated and prioritized interface and implementation of various signals. We have the end customer, who can be the connection user or the connection subscriber, who has different contracts. Let's say if you're the house owner or the home owner, you have a contract with the grid operator to enable the grid connection. And then if you're the connection user, you have a contract with the market actor, which is an energy supplier or an aggregator, to ensure your supply or to ensure your marketing of your flexibility. And then the grid operator and the market actor also can have a contract where, for example, reduced grid fees or dynamic grid fees are implemented. The solution dynamic pricing always works when there's a green phase, let's say, in the grid. So we have time variable tariffs that stimulate the consumption or production of certain devices or buildings, which might lead to a high simultaneity. Then we need, let's say, a fire brigade with our solution power limitation, or 14A solution, as defined by German law, where the DSO can send power limitations to the grid connection points to then reduce temporarily the consumption of certain devices. And to, let's say, prevent all these fire brigade or last ad hoc measurements, there's a solution of flexibility provision where, through a monetary remunerated access, this fire brigade can be avoided, or the need for power limitation, by sending incentives and power envelopes that forecast or that prevent certain grid congestion cases. And the self-consumption optimization can run parallel to all these processes. If you want to learn more on a deeper level how all these use cases and solutions and different actors and domains work together, we have written a white paper that you can see here. I guess the slide's going to be shared afterwards, so you can just use the link where we explain in more detail what you have to consider from different perspectives, from the aggregator side, from the DSO side, from the device manufacturer side, and the energy management system. Where to experience EBUS? EBUS is already implemented in quite a lot of energy management systems and smart devices that are available on the market. We are working together with several partners in various research projects where we have implemented the EBUS interface already and do large-scale testings. And also, from the automotive industry, there is a pretty positive attitude towards this standard to be implemented as the language for energy to connect the automotive industry, meaning wall boxes, to the energy management system. With regard to standardization, EBUS is pretty active in the cooperation, or in cooperation with several alliances and consortia out of in Europe, but also abroad in the United States. So looking to the grid connection, we are working with OpenADR to align those protocols and use cases with the EBUS use cases, so that if let's say, power limitation is sent by a grid operator using OpenADR, that the energy relevant devices inside the building understand the signal and that it's mapped to EBUS and fulfilled inside the building. We work with SMIC from the metering industry and with CHAR-in to align the use cases concerning automotive and e-mobility. And also, as you can see in the picture, we're in conformity to and have a single interface to the home automation and also to OCPP. So these are not either or, but you can have an entire architecture and system running with all these protocols and alliances. This is an overview of the standards and standardization committees that we are working with and working in. In green, you can see those standards that are relevant for EBAS and relevant for the entire ecosystem, and that we are already in collaboration or different research projects trying to find a way how to map and align those standards. The blue one are international standards where EBAS and the use cases and data model is already included. And the light blue one, or rather violet ones, are the German or national standards where EBAS is already set and defined as a norm or as a standard. To assure interoperability, we follow the semantic description of ETSI with a number that you can see here. Some of you maybe know it under the name of SAREF. In this case, it's SAREF for ENA. And this is also one of the, let's say, homework for our next years that we want to push and drive the SAREFification of the e-mobility use cases, of the EBAS use cases, and align the EBAS standard with those protocols and allies that I've written here. And now, last but not least, I want to give you an insight or an example of where EBAS was active or is still active in an EU project. It's called Interconnect, which digitalize or which works on the digitalization of energy management solutions and holistic and interoperable approach to energy services. With more than 11 countries, meanwhile, and 50 partners, it's a quite large consortium. And EBAS was leading, or is still leading, because the project was extended for a year now, is leading the German pilot, more specifically the pilot in Norderstedt, where more than 50 households are participating. We're using, or we have implemented, a productive smart meter gateway infrastructure, and we are testing variable electricity prices and power limitations that are following the grid demands in accordance to or with 14A. The entire system and infrastructure at the grid connection point is following the IT security requirements, and we are using a standardized data model and use cases that are following the Federal Network Agency requirements, as also mentioned in the related documents of those institutions. We can achieve a reduction of the total load that is generated, or in this case not generated anymore, as we're using price incentives to shift the load or to reduce the load and to increase the energy efficiency by self-consumption optimization. And we also collected quite a lot of learning or outputs of the installation process when it comes to connect those flexible loads to the digital grid connection point and to the control units directly or via an EMS. This is an entire process that has to be designed and developed, and also applications and devices have to be developed that are making this process, or that are enabling this process on a large scale. Then we have the challenging part of the project, which was the harmonization of use cases and protocols and business models. So once you have so many partners in different countries with different regulatory requirements and ideas of the participants, you see that there's quite a large variety, and that this variety is not applicable from one country to another country. The use of proprietary versus standardized connectivity made it hard sometimes to apply or to adopt the architecture and the approach of one country to another country. And the look at the control of devices, so the last unit that is actually telling a device how to behave was sometimes solved in a cloud solution, sometimes in a local energy management system, which made it hard to replicate on on a large scale. So lessons learned for such big projects and for the scalability, it is wise to embed standardization from the beginning and standardize use cases and standardized data models. And yeah, it's also recommended to have industry partners who are interested in implementing standardized use cases. Otherwise, it will be hard to adopt to serial products after the project. Yeah, with this, I'm going to end. And yeah, I'm looking forward to get in discussion and in contact with those of you who are interested. And also a short advertisement from our side. We are holding, or we're going to hold a webinar on the 21st of March, where we're diving a bit more into detail about the dynamic pricing solution and dynamic tariffs and how this can be enabled with the EBAS use cases. And the link for the registration is going to be posted on LinkedIn. So if you follow us there, you're going to be up to date about how to join.
Thank you.
Yeah.
Thank you.
Maybe just some sentences regarding Smart Innovation Norway. We are a research institution and we're located some 100 kilometers south of Oslo, so right at the Swedish border. And our history basically dates back until 2007, 2008. And at that point of time, the Norwegian government said, we see a lot of changes in the telecommunication industry. And we expect that we will see similar changes in the energy industry during the next 10 or 15 years. And therefore, we received some seed funding, started as a Norwegian center of expertise for smart energy markets. And the reason for that was that in our small town Halden here in Norway, we also developed some ages ago the first international power exchange. So Nord Pool was basically developed in Halden. Therefore, we had a cluster with a lot of energy-related experience, and therefore we received this funding and grew during the last 15 years to some 70 employees, which are active mainly in research projects. The Sender project itself is supported by the European Commission under the Horizon 2020 program. And the abbreviation Sender stands for Sustainable Consumer Engagement and Demand Response. And as we wrote in our project application, we want to put the household consumer at the heart of the energy market. And therefore, we also focused very much in our project application on co-creation processes where we can work together with the consumers in order to create solutions that they really want and desire for their daily lives. Nevertheless, of course, we cannot do this alone, but we need also a lot of technological partners, and therefore Sender has 15 partners. Smart Innovation Norway coordinates the projects, and then we have some additional partners which are spread all over the Europe, from Finland in the north down to Spain or Greece in the south. So these companies work together to realize basically a structure which is outlined on the next slide. So we intend to develop technology innovations, and this in the field of supply and demand forecasting algorithms with CRS4 from Sardinia in Italy. We implement a very advanced smart water heating system, which is also in households, of course, a relatively high load appliance. We apply a concept from previous projects called building as a battery, where we try to use thermal storage, and the partner who is responsible for this task also develops a so-called Sender Smart Box, and the Smart Box basically connects, as shown on the right-hand side on the graph, connects all the devices which are related to the project activities and allows for central steering. Another interesting part, consumer digital twin from Paracon in Greece, stemming from the aviation industry, gives now the opportunity to develop a very good forecast regarding the occupation of buildings. And in addition, we also, as discussed before, have a peer-to-peer trading system in the project, and also, of course, have a front-end application for the household consumer so that he is in the position to control via an interface on a cell phone all the devices which are connected in the project. As I said before, although we have all these technology solutions, I would like to focus, and was also asked to focus, a bit on the consumer engagement approach. So how do we motivate consumers to participate in our projects and play an active role, as also required by the Commission, which opens these calls that we applied for. I think one very basic democratic approach, which might be related to the Nordics, is that from the beginning of each project, not only European projects, but also national projects, we try as good as we can to involve as many stakeholders from various different stakeholders group. For that concept, from a methodology point of view, we apply a so-called quintuple helix. So we integrate academia, civil society, environmental activities, industry, and government into our projects. And then we try to pick out the most relevant stakeholders and go with them through a stage where we start from a proposal phase and then analyze, define, develop technology, test the developed technology, evaluate it in demonstration sites, and then replicate them for commercial use. And that's our standard methodology approach. And that's also something where we can involve on a, let's say, meta level, very relevant stakeholders for our projects. In the next step for the tender project, we tried to develop so-called consumer ontologies. So what kind of consumers do I have in the environment of our 3 demonstration sites, which are located in Finland, Austria, and Spain? And we basically found out that there are 4 main groups. On the one hand, a core group for us are ecological aware persons, which pay a higher price for green electricity and therefore also seem to be more likely to actively involve in innovative energy projects, which might lead to a green energy transition. On the other hand, not that interesting for us, cost optimizers with low ecological awareness. So we basically excluded them from our co-creation approaches. Instead, we also integrated persons with a strong technological knowledge and curiosity, which also identify themselves with the region and therefore can be kind of multiplicators for energy community setup activities, for example. So also this is a very interesting target group for the consumer co-creation. And then the 4th group in the order here, and the 3rd group that we integrated are the ones which are very regionally rooted, because they are usually in projects also very good ambassadors to take the project idea into their neighborhoods and acquire additional participants for the projects. We then, after selecting the stakeholders and the consumers, household consumers, we typically run, as well as in the sender projects, through 3 different phases. So the first one is the recruitment phase, where we disseminate a lot of information material. We create events for household consumers. We also try to have newspaper publications to create awareness for the project. Then we have the consumer response phase, where we once more try to roll out to interested persons the relevance of the project, especially for the green energy turnaround, and that in a kind of bottom-up approach. And finally, the 3rd phase is basically now ongoing, as we are at the beginning of the 4th year of the project. So the persistence phase, where we try to keep all interested consumers on board and use incentives for them, create seminars, do demonstrations with them in order to keep their very good motivation and activity that they show. In addition, for the first time in the Sender project, we created a so-called co-creation steering group. So based on the experiences from previous EU-funded projects, we said, how do we really get to a solution where the consumer has a say and where the consumer can decide together with tech experts what kind of solutions shall be implemented at the various demonstration sites. So for that purpose, we created this co-creation steering group, which consists of experts of the consortium, of course, of consumers, distribution system operators, and also technology developers. And we use social innovation tools in order to bring this group together at the 3 demonstration sites, share their views on the required outcome of the projects. Our experts then showed the technological limitations. And based on this very close cooperation in this co-creation steering group, we then went into so-called co-creation workshops, where local teams of consumers and experts analyzed the circumstances at the demonstration sites and then decided what they want to see implemented at their pilot site of the project. And this basically led to a selection of 5 different use cases that we defined together with the household consumers. On the one hand, we called it residential explicit demand response. So that was one of the core wishes of the involved consumers. Then another wish was to maximize the use of renewable energy sources. So we developed a second use case dedicated to this objective of the involved household consumers. Then, of course, to minimize the electricity bill. Remote steering and control of household devices was also very high up on the wish list. And then also, as we heard before, peer-to-peer energy trading, that I can basically exchange surplus electricity from my renewable generation with a neighbor, was also one of the 5 use cases which was selected by the household consumers. And what were the consumer engagement lessons learned? On the one hand, I think we managed to have a very high involvement of the consumers. As I said, in Austria, we are talking about a very small town with some 25,000 inhabitants, and we reached 250 involved consumers within half a year. So that's more than 1%. And I think something where this Austrian team can be very proud of. Another thing based on the very close communication with the households is that even critical applications like digital twins, which are seen with a kind of suspicion from many household consumers, we were able, based on the setup of the consumer engagement, to outline the data privacy issues which are built in, to outline what the system does, to outline that no data which is personal will be shared. And based on this very close communication with the involved household consumers, we also managed to implement this technology and did not see the typical criticism or long discussions, but the communication served also there for a purpose. Another maybe, let's say, critical factor, if you integrate household consumers, if they are really motivated, then it's a problem if we see crises like the supply shortage from China for technological components. And then we, as a project consortium, created high expectations at motivated household consumers, but then we don't deliver on time. Therefore, motivation might get lost. Therefore, we tried to communicate regularly with the consumers, explain to them that the lack in implementation is not about them or our motivation, but about technological supply part problems, and that also in a way worked out in a very good way. And then, as we also heard in the presentations before, then if it comes to the hands-on implementation of the Sender box, so to speak, of the project results, then we also experienced a number of surprises where the first technical audit did not see everything. So we have to admit that the technical implementation process for this household consumer demand response solution took longer than initially expected because it was not as streamlined and easy as we expected initially. And to sum up for the overall project and not only the consumer engagement, what were our key takeaways? On the one hand, regarding the regulation, we saw that in the initial slides of GRAPPA, Finland was one of the blue countries, which also reflects our project outcome. So in Finland, we had a very smooth integration of all technologies from a regulatory framework. Austria provided some barriers, and we see massive, also later on commercial implementation challenges in Spain based on the regulatory framework. Regarding the demand response technology implementation, also something what we did in this project for the first time is that we cooperated with the Austrian Institute of Technology, AIT, and they developed the so-called virtual lab. So all the components that we rolled out at the demonstration sites were tested, and especially the interoperability was tested in a virtual lab. And once we were sure that the customized solutions for each of the 3 demonstration sites work together, are interoperable, we then started the rollout, and that was an experience which probably avoided a lot of delays by technical problems. Business models, we are currently evolving commercial offers for household consumers, and we apply a joint exploitation approach. So the cooperation within the project will also continue after the project, where we will do our best to have some commercial solution that we can then bring into the market. Consumer engagement, as I said before, very positive approach, and this approach obviously was also in a way realized outside of our project context, and therefore we received now for the social innovation part various invitations, also for example in the net zero building environment. So therefore, I think the realization that demand response implementation is not only technological, but also a very social process is growing, and therefore also the results of our project in this area receive a lot of attention. And finally, regarding the aggregator cooperation, for us, I have to admit it was a bit challenging. We were one of the first household consumer-related demand response projects, and therefore the volumes, even with some 200 household consumers, with some PV installations, some batteries, the volumes that we can provide in terms of demand response are relatively low, and therefore we face the challenge to find aggregators that intend to work together with the project in face of the quite low volumes that we can deliver to them. Thank you very much.
Pablo to drive the question and answer.
Thank you, Matteo. Just for the speakers, can you stay maybe 5 minutes more or so? Maybe, well, 10, let's say, to be realistic. So that okay? Okay. Just we can go maybe take 3 questions. Sorry for maybe in the meantime, you feel free to answer in the chat if you want to answer some directly. Maybe I will start with Marcel. There was one from, it says if aggregators participate in the market, it will be still use DSO network. So how can it provide congestion services to the DSO if it is one of the actors causing the congestion? It's kind of the chicken and egg problem.
Yeah, that's indeed a very good question, which we have considered as well. It's one of the challenge, or like part of a challenge, because if assuming you have a virtual power plant and saying you causes this problem, then you cannot come with a solution at the same, because this will lead to like problems which you can see in that game theory as well, where you identify similar situations. And this is why coordination is especially needed, because you have to, or you need to see and monitor, for example, if a TSO activates thousands of electric vehicles and the TSO or the aggregator provides the services and causes the congestions, there needs to be a coordination mechanism which relieves the congestion or relieves this issue. Because assuming like this 1,000 electric vehicles causes damage on a transformer or in a grid, it will lead to the situation where the TSO is maybe satisfied, the DSO, the aggregator is satisfied, the active customer as well, but it destroyed the transformer and the distribution grid. Therefore, it's a reason why we need coordination and more observability, beside having the issue of that in the current situation that the aggregator can like solve the issue and make the issue. Therefore, this is one reason why we need this coordination. I hope it
Okay.
clarifies.
Yeah. So for, I don't know if someone, well, maybe I relate the question very quick. So for implementation, does it mean that an aggregator VPP will have the network information of the DSO? Feel free to answer, or someone, yeah.
Yeah, it's not that you require the whole topology or the grid itself. It's just like this basic data, which are like how much, or like the grid connection point, how much power I can transmit through it. It basically depends on the fuse which is installed. But nevertheless, it's not like that you have to transmit to a grid operator, to an aggregator, the grid data from the whole area. It's just like you require an information exchange about the congestion, if there's a congestion, or the physical connection point, which I think Ibas explained as well, like Annika said. You require that kind of information, how much power you can inject or withdraw from the grid.
Okay, thank you. So I think this goes to Jurapa, but feel free, yeah, if someone else wants to comment. So aggregators have access directly to the resources via proprietary interfaces. So this is not too much restrictive. Why to use proprietary interfaces and not the standard ones, such as, for instance, a SIM-based interface? Well, Jurapa, but I think Annika also you can comment on this.
Yeah, as mentioned that the aggregator can provide, their solutions, and that could lead to the proprietary protocol or solution, and then for the vendor login at the end. So that's why we identify these challenges when we have identified the coordination approach and what existing that the aggregator already provides some services. Some of them already apply the standardized protocol that have been using for their services. And this is something we would like to encourage, for this technical challenge, that we should agree or have the regulatory framework that define this kind of the standard coordination approach, how it should be. So at the end, it would benefit to all of the stakeholders. For example, DSO, TSO, and also the customer itself. So we don't want at the end that you use one solution, and when you want to switch to another solution, it's not working. You have to invest on the new system. That is something that's going to increase the cost for the customer, and then it will make them feel that it's not user-friendly. This is something that we would like to avoid when implementing this kind of the new energy services. So the technical requirement should be in place and should use standardizations, and this could solve everything that we are afraid of.
Thank you. And this one, yeah, for Annika, this for sure. How active are big names such as Apple, Google in EBOS? Are they involved somehow, or have they been involved? Sorry, Annika, you're muted.
Sorry. Yeah, I just said if they were, I guess everyone would have heard about it. No, they're not involved. yet or not at all. Let's see how this is developing, because so far, at least in Europe, we haven't perceived Apple or Google to be or to provide a standardized interface to connect single controllable devices to a standardized protocol from a grid operator or a market participant. So we haven't really seen that there's any other than home automation. That is totally their business, and they're good in it, and that's good, and they can continue doing this. But for the energy management relevant devices and the standardized connectivity to grid operation or to grid protocols and aggregator protocols, we haven't seen them playing a role. We had a cooperation with Microsoft and have demonstrated some use cases, but we see that there is a bigger demand or bigger need to work with those players who are integrating the interface into their devices, and those who are interacting and play a relevant role at the grid connection point, then looking into home automation and AI systems.
Yeah, maybe now that Annika, you are answering was a related questions on communication standards. So why the international IEC 61850 is not proposed to be used? Maybe.
It was actually.
Okay.
It was on my slide. I can just quickly refresh it. Let me share my screen again, because it's, I mean, these slides with all these standards and protocols is pretty confusing because it's just a lot, but we are also active in a lot of standardization committees, so that is fair enough that those questions are arising. Do you see already what I'm?
At least it's black for me, and I'm not sure.
Let me just try again. Okay, black works. No.
Yeah, now.
So the IEC 61850 is just over this OpenADR protocol, which is a surrounding protocol, but it's pretty standard in German to be applied, and we have a mapping, or let's say a conversion of this protocol and the signals that are included in the protocol to be then converted at the grid connection point, the latest to EE bus communication. So EE bus is consistent or in consistency with the IEC standard here.
Perfect. Thank you. Maybe I will leave this one open to any of the presenters. One of the last ones, will DSO coordination create incentive for DSO not to invest in their infrastructure, but to focus limiting usage? This is.
It depends. If I understand correctly, then the question correctly, it's often referred to like this fit and forget approach, to make like big copper cables and make it as big as possible and only covering the biggest use case or like the biggest peak demands. However, a lot of, or as I am aware of, there are studies who argue that it does not make sense for a renewable or sustainable energy system to have like investment only in grid infrastructure and suitable for the peak demands. It makes more sense to control devices and balancing it instead of just investing in more and more copper. But for example, the regulation in Germany has as well the restriction that grid operators are not allowed to regularly shut down the controllable devices, which means like you're not allowed to control like each day or so, but as soon as you're controlling the device, then you have to say to the federal grid agency in Germany, you have to prove that later on you will do these grid investments and not like operate in a way that you say that I have minimal investment costs and I will always control down all the devices in the distribution grid. So basically the incentive should be to have the flexibility, but as well to avoid that you control all the time. So basically it's like both versions, like either only controlling or either only investment in bigger copper cables. Both versions are not ideal, so a mix out of it is one of the most economic value, or has the biggest economic value.
Yeah, related to this, sorry, just a follow-up to clarify this possibility now that DSOs can control directly and limit. Does it have a compensation? How is this established?
Yeah. For example, in Germany, the first phase is currently that you get between 100 and 200 euros per year to provide the access to the device itself without controlling it. It's just like you get this predefined kind of fee from that the grid operator pays you 100 to 200 euros. Then you are controllable, but only for worst case situation and not like for regular ideas. And in later step, it should be dynamic grid fees, which will be as well in the next years. But currently, it's only this fixed one, which is rolled out. Or will be rolled out.
Perfect. Thank you very much. Yeah, maybe a general questions and maybe Christian and it says in your demos how baseline was set. Have you focused on this computing the baseline?
I don't get the question. The baseline.
Yeah, the baseline basically is the profile, the customer profile without taking into account the activation of flexibility. So the profile previous the activation of flexibility. If you have computed this in your demos.
We finalized that at one demo, and we are still in the process at 2 demonstration sites. Yeah.
Okay. And is there any particular methodology that you have been using for that?
That was done by our partners from AIT, and they have a certain model for that.
Okay. Okay. Thank you. Yeah, maybe last question. Sorry for those that couldn't answer, but please, if you want to answer in the chat, you can do that. In your demos, how was guaranteed that the capacity is not sold twice, for instance, to the local market and to the wholesale market? As in any of the demos, have you looked at this?
In our demo, we have only a connection to one aggregator or DSO at each of the demo sites, so therefore that would be their problem, but we only sold to this one, let's say, general partner, because it was difficult to find more than one partner for these small volumes that we had to offer.
Okay. This is always a question, and I imagine, well, sometimes the issue is that one activation can serve the needs for different entities. No, this happened in the cascading DSOs, or even if you provide a service to a DSO, also this could be beneficial also at the TSO level. So to what extent the resource can be rewarded twice, or how to do this in a optimized manner. I would say that as well depends on the market models, the coordination models that also were presented at the beginning. Okay, I think we more or less arrived to the end, a bit late, but I think it was a good presentation. Thank you for the presenters. I remind you that all the material and the presentation also will be recorded in our ISGAN webinar series on YouTube and also in ISGAN website. So please also register as well for following webinars. So thank you everyone, and have a good rest of the afternoon.